Hello, good evening. It's a pleasure to welcome this evening's speaker, Hans-Arno Synal. Hans-Arno is the head of the Laboratory for Ion Beam Physics here in our department, and he has been awarded the title of professor by the ETH Rat last year. Congratulations, Hans-Arno. So let me shortly introduce him. He studied physics in Bonn and at ETH Zurich. He made a postdoc here in what was at that time the Laboratorium für Mittelenergiephysik. Then in 1990 he moved on to the PSI to become a research scientist, working in what was then a joint lab between ETH and PSC, the Laboratory for Ion Beam Physics. So that is where he came into this lab and moved up the ranks, became a group leader and later deputy director. And in 2008, when Martin Sutter retired, and actually we also had to reorganize the lab moved fully to us, to the Department of Physics at ETH Zurich. At that time, we were happy to find in Hans-Arno the new director of this lab. Now, what is the mission of the lab? It's rather broad. Essentially, it's C14 radiocarbon dating, but it has expanded enormously over the past 10, 15 years. Radionuclides of all sorts are analyzed in the context of the environment, geology, pharmacy, medicine. And besides this science perspective, there is a special love of Hans-Arno, and that is to build new machines. And I guess he will also tell us not only about the art of dating, but also what new kinds of machines he's building to pursue this art. Please, Hans-Arno.
Yeah, Gianni, thank you. Thank you very much for the nice introduction. Of course, it's an honor for me to be here in front of the physics department and the students. And the topic of my talk today will be the art of dating progress in radiocarbon detection and related applications. The first part of the title had not space on the placard which was sent around, and art of dating might be a little bit with two cents. You know, we all know that there are four fundamental forces in nature, and of these fundamental forces, of course, strong interaction is the strongest, but for our personal life, the attraction between male and female is more important, and in this sense, maybe the art of dating can be misinterpreted. Anyway, what I'm going to talk about is about real datings, and you have certainly heard about things we have done in the past, and here I show you just a few examples of things which we have dated in the lab, which went into the newspapers. Let's say the Bamiyan Buddha statues, which had been exploded by the Taliban. They were made of stone in the rock of this rock things, and they were not only excavated just from the rock itself. They were cladded with mortar, and in the mortar there were some kind of composite material introduced. You know, they used like straw and organic material to stabilize the mortar to form the nice shape of these Buddhas, and by having organic material inside of these compounds, we could access dating information from that. Or maybe you have heard about this 10,000-year-old tree which had been excavated in Schlieren quite some time ago this year, and in order to match it into the real lifetime of its existence, radiocarbon dating is applied, and we did it here at ETH. Or another thing which was in the newspapers was the excavations which had been done in St. Gallen, and there was a stone coffin found, and bones from a person was found, and we could really establish the age of these bones. So these are things which are in the newspapers and which we are doing. And if you've not heard about this, you have certainly heard about this person. And this is the Iceman. And in order to show you with what we are dealing, I brought a little piece of it. And I show it around. So when you leave this room, I would like to have it back, and everybody could touch the Iceman. Okay, what kind of technologies, what kind of methods we are using for our dating research? And there we have a technology which is called accelerator mass spectrometry. And this accelerator mass spectrometry is a technology which enables us to detect individual atoms. We have a single atom counting technique, and we can identify individual atoms. And we can do this with high accuracy and over a huge dynamic range. What we typically do is we measure isotopic ratios between 10 to minus 9 and 10 to minus 15. And what this means is shown in this graph. You know, if you have a grain of sand which is 200 by 200 by 200 microns, and you have this grain of sand which is a little bit heavier than all other grains, you have to find it in a cube 2 by 2 by 2 meters in order to have 10 to the 12. And that's for us the starting point for many applications, for carbon, especially for carbon. That's the starting point. And our sensitivity goes even 3 orders of magnitudes further down. Another example of what 10 to the 12 is meaning is you think of a coin, just 1 franc. You know, I put a franc on the table, and you imagine you have 10 to the 12 of these coins. That's the whole, let's say, loan which Italy has taken from all people. And you think I pile all these coins on one pile and put in the francs just €1. And then you have to select the euros from the francs. And you are a very experienced person. You can do this by doing 3 per second. You have to do it for 3,000 years, all night long, all day long, to find 1 franc in 10 to the 12. So that's what our capabilities are in respect to detect single atoms. So having a detection technique which has the power of these kind of minute quantities to analyze, it's not so easy to apply it. Because when you look in the abundance of all the elements we have on Earth, and this is shown in this view graph, you see in this view graph, we have normalized the concentration of all elements versus against silicon, and then you see here are 3 orders of magnitude, 6, 9 orders of magnitude, and in 9 orders of magnitude, you have almost everything you can imagine in any compound. So having such a tremendous sensitivity, it's not so easy to really use it in a way. But fortunately, we do not have not only stable nuclides, we have also radionuclides. And here you see just the number of natural radionuclides just listed here with their half-lives, and they, with a red circle, these are the nuclides which have a specific origin and which can be used for many purposes. They are produced in the atmosphere, most of them, and the most important ones are radiocarbon, beryllium-10, aluminum-26, chlorine-36, calcium-41, iodine, and also the man-made actinides, plutonium, uranium is of course natural. These nuclides are produced by the cosmic radiation, and they introduce into the geochemical cycles. And so we can use these nuclides as natural tracing substances. Of course, the most important one is radiocarbon, and in the following part of my talk, I will just focus on radiocarbon. There are many other applications with the other nuclides, but it would be too much just to bring it together. If we look for the detection of radionuclides, the first thing which comes into the mind of the people is, of course, to use just the radioactive decay to measure these isotopes. And that was also the idea of Wilhard Libby, who measured the C14 concentration of a number of known age objects and found that the radiocarbon to carbon ratio is just going down exponentially for these known age objects. He initially thought doing this in order to establish a new half-life of radiocarbon, but then it was found out that it can be applied just to date organic materials. But if you want to date or to analyze a sample according to its activity, the number of atoms you need is directly or inversely proportional related to the decay constant. So the longer the half-life of nuclide is, the more nuclides you need. And if you go in the numbers and say, I can measure maybe for 10, 12 days and have a background counting rate of 1 event per 100 seconds and a good detector. So I need quite huge amount of atoms in order to make appropriate measurement. This problem you can overcome in a way when you're not waiting these nuclides to decay, but you can go and directly count the individual. You filter against these different species and directly count these atoms. And in this case, the number of atoms you require is not depending on the half-life anymore. It's just depending on the efficiency of your filter system, of your detection system. And in our case, we have some kind of negative ion formation, detection efficiency, and the transmission of our instrument, which is involved. And when you go through the numbers, then we end up with efficiencies of the order of a few percent. And this means we are, compared to the decay counting, at least 4 orders of magnitude more sensitive. And this means we can go to much smaller sample sizes and can analyze, let's say, the Ötzi or so in just tiny little amounts. This is in principle very nice, but like everything in nature, nothing is for free. You have to imagine that in case we want to do this, we need a filter system which is able to resolve this huge dynamic range, 1 in 10, in 15 orders of magnitude. And in general, when we want to separate radiocarbon from normal carbon, C12 or C13, it's a simple task with a mass spectrometer, because the mass differences between the stable isotopes and carbon-14 are huge. But there are other species. And the first one, which is of importance, is the nitrogen-14, which is the nuclear isobar. And when you're looking into the mass difference between carbon-14 and nitrogen-14, the mass difference is only 1 in 80,000. Of course, a very high-resolution mass spectrometer is able to resolve 2 different species with such a low mass difference. But the intensity of nitrogen is 10, 15 orders of magnitude more than what you get from carbon. So it's hopeless to do this. In this sense, we have to find a way to get rid of the get rid of the isobars, and in case of carbon, nature is in favor with us. Nitrogen doesn't form negative ions. And so by using an instrument which uses negative ions, we can just forget about the isobaric background from the nitrogen. On the other hand, we need to suppress the neighboring masses. They have much bigger mass differences, and with a multi-step conventional mass filter system, this is of course possible. In addition, we need what we call reliable normalization. On the one hand side, we just count the individual atoms, but we need to normalize the counting rate of these C14 atoms to the amount of carbon in the sample in order to get an isotopic ratio. So we need a reliable normalization process. And the last and let's say, remaining most important step to follow is that we have to eliminate equal mass interferences. These are molecules, C12H2 or C13H molecules, which have quite large mass differences, but they have, in a way, much higher abundances in a negative ion beam. 10, 11 orders of magnitude more of these molecules are available. And so we use a process where we start with negative ions, accelerate these ions to high energies, and then collide these ions with neutral gas. And in these collisions, we strip away the binding electrons of these molecules. And so when I go to charge states 3+ and higher, they just disintegrate from Coulomb force. So there are no bound states in the 3+ and higher charge states. And so we can really get rid of these molecules. There will be a second and even more important process that these molecules can be destroyed even in a low charge state where bound states for these molecules exist. But how does now such an analysis would work? You know, we have our mass spectrometer, we introduce our samples in the ion source, we produce negative ions, and by producing negative ions, we just filter against the isobaric interference of nitrogen. We analyze the beam in a conventional mass spectrometer, it's a magnetic field, and we analyze for mass 14. And then we have in the beam only mass 14 particles, which are molecules and C14. We accelerate those ions to high energies and collide them with neutral gas to destroy the molecules. And then we use the positively charged atomic ions fraction of these molecules and analyze them in a second mass spectrometer. And in the end, we detect individual atoms counting in a gas ionization chamber and look at the signals they produce from their energy loss to identify them. For the normalization, we inject in short pulses carbon-12 and carbon-13 stable ion beams and measure the current of these ion beams in Faraday cups, and by normalizing the counting rate of C14 to the measured currents, we can just get the isotopic ratio. So that's a basic principle of an AMS system, and this has been invented 35 years ago, but we have, let's say, improved this technology significantly. Looking in the today's world, you see here these red spots of all AMS systems in the world, and there are about 100 systems running. On a commercial side, you can just buy these instruments from two different companies. The one company is in the Netherlands, and the other one is in the US, and they provide instruments for this purpose of different sizes, based on very huge accelerators with 5 and 6 MeV terminal voltage, or smaller ones with 3 or even 500 kilovolts and even less. So what is defining the size of the accelerator system suitable for your analysis? And this comes with the yield of the specific charge state you have. You see in this view graph the fraction of ions which go in a specific charge state after a collision through a gas as function of the beam energy. And if you want to reach high efficiency of about 50% for charge state 3+ or higher, you need to bring them at least to 2.5 million volts. If you want to 4+, you need to go at least to 6.5 MeV of energy. And this means big and huge accelerator facilities. So these instruments are nowadays installed. Let's say here's an example of an instrument in Rossendorf in Germany, coming to operation quite reasonable. Of course, in order to make these installations, they are still 25 meters long instruments. So it would be, of course, nicer to make them more compact and more easier to use. And what you would like to do is to operate in a way where you can use the 1+ charge state. Then you can go with a maximum yield in argon or nitrogen stripper gas at about 450 to 500 kiloelectron volts and make it much more compact. So since 1+ stable molecules will survive this process, you need a different kind of process of destroying these molecules. And this is shown in this view graph here. You know, I have here the stripper medium. We start with the negative ions which introduce into the stripper, and they are, of course, some C14 ions, but the vast majority are these molecular ions. In these processes, you have a number of collisions, and in these collisions, you have electron loss and electron capture. And this you can see here. This is the yield of the different charge state as they evolve when they make more collisions in the gas. When we start with 1-, the 1- is decaying until it's stabilizing, then the neutral is populated and the 1+ is populated, and to a certain fraction 2+ and 3+ as well. And you see, after a specific density or after a specific number of collisions, this will not change anymore, and we call this equilibrium charge state. You know, this differential equation which describe this process will come into equilibrium conditions. In these collisions, we not only have capture and loss processes, but we have also a molecular breakup. So if a molecule will collide with a gas atom, end up in charge state 1+, there is a certain probability of breaking these molecules apart. And this is described by a simple cross-section. And when you look here for the intensity of the mass 14 ions as function of collisions or density of the stripper gas, you see that the intensity of the molecules goes exponentially down until you reach the final C14 atoms. And they are stable. They do not change anymore. So when you can operate your machine in a regime where the density is high enough that all these molecules are gone, you can go to the 1+ charge state and build a much more compact system. And this we have done some years ago. Based on a 500 keV Pelletron accelerator, we have demonstrated that such a principle is working and can be applied for radionuclide detection. We have done this in collaboration with National Electrostatics Corporation, and they had now the right to commercialize this kind of technology, and they have built their own instrumentation, and it's distributed and commercialized in the world. And the competitor, they invented a similar system based on a 1 MV accelerator of their fashion. So that was the one stage, but we were always looking into optimizing this kind of process further. And in order to do it, we looked into the physical properties which are behind this technology. And of course, the cross-section of molecular dissociation is the key to find an improvement in the technology. And you see here these cross-sections in argon as function of energy of the ions. And you see that this cross-section is just decaying a little bit, only a few %. So if you can go to energies of about 200 kilovolts, you're still able to break up the molecules. But on the other hand, when you go to lower energies, the interaction of the beam with the stripping gas gets more severe, and you have to, and the beam gets straggled, angular straggled and energy straggled, so that your system needs to be able to handle large emittances of. Anyway, we did this, and we invented a new concept, a vacuum-insulated platform, which is not an accelerator anymore. And you see here a sketch of this device. This is a stripper volume where we flush some gas inside, and we pump it differentially with big pumps on both sides, so that the negative ion beam, which is accelerated in these gap lenses here, can be destroyed with the molecules, and then the positive ions are extracted on the other side. So the high voltage is provided by just a commercial power supply, which you can buy, and feed it with a cable into the vacuum system, and the high voltage, which is applied to this stripper housing box, is insulated against ground potential with just a vacuum. This makes the system very, very compact, and based on this idea, we set up the so-called MICADA system, mini carbon dating system, which fulfills all the requirements of a compact lab arrangement. It's not the only development which has been done. The company NEC, they went in the same direction, but they got rid from the tandem principle. They just put one part of their spectrometer in a high voltage platform and analyzed the beam after they have been destroyed in a stripper canal just on a high voltage deck. This makes the system operational at 200 kilo electron volts as well, but it is much larger and less, let's say, useful for a normal lab requirement. At ETH, we are running our system now, and these are the numbers of analysis we are doing we have done in the last year. So about 5,500 samples are measured in routine operation, and we achieve with this small compact system, which is more like a mass spectrometer than an accelerator-based system, performances which had never been reached before. So overall, we are able to get uncertainty levels for isotope ratio measurements of the order of 1 to 5 per mil. These instruments we have built for us, but we not only built these instruments for us, we also, in collaborative projects, we build instruments for other partners. And at present, we have 7 instruments in the world, the one in Zurich. Then we had a dedicated system for biomedical applications shipped to the US in Davis, California. And then there's one instrument in Mannheim, another one in Hungary. Very recently, we installed one in Seville, and there are 2 more machines right now here in Zurich, which one is dedicated for Bern University, and the other one will go to Brussels. When you're looking into the world distribution of this kind of technology, then you see here those which are marked in black are based on the traditional way of making AMS. And they are marked in red, which are based on the technology we invented here at ETH. And you see right now, we have about 50% of the shares of all these instrumentations are based on the technology we invented here in the last years. And this is even more strong when you see how these different kind of instruments evolved over the time. And in the very beginning, in 1978, AMS was discovered at huge facilities. And then there was a period where the nuclear accelerators, which were available at that time, were transferred into AMS systems. And they were operated, and they are still in operation. And we in Zurich have still one of these instruments available. But this new technology has really gained importance in the last 3 years, and I'm sure that this is not the end of the trend. So by comparing what has been possible at the very early stage of AMS, we can compare the size of the instrumentation which was required to make C14 dating analysis. And compared to the instrument we have now available, it would fit just in the ion source of these big instruments. Reducing size, complexity, and instrumentation, then there's one law you have in mind, and that's Moore's law. We all know, and we were very proud to have the first Pentium processor on our desktop. And when you see how many transistors go in a modern CPU, in a handy or in an Apple, then it's incredible. And it's very impressive to see that this is growing on a logarithmic scale. To translate this in AMS, we would just say what kind of beam energy was required at the beginning of AMS technology. It was about 50 MeV. And then there were different steps, which one most important step was the reduction from the 3+ charge state to the 1+ charge state, and then these newer instruments, which went down in a regime where you could operate them at 200 kilovolts. So there's quite a good exponential decay in beam energy. And the question is, yes, can we go any further? And in order to go any further, like always, the key is the understanding of the physical principles behind. And I said it earlier, that the cross-section for the molecular dissociation is of primary importance. And you see this here, the destruction cross-section for these two molecules of relevance as function of beam energy from 240 kilo electron volts downwards. And you see that this is very stable, but if we go below 100 kilo electron volts, it will break down in nitrogen. Going to lighter gases, the situation is a little bit different. Having helium as a stripper gas, we don't see the decrease of the cross-section. And the cross-section itself is about half the size of the nitrogen cross-section. But you have to keep in mind, per atom, it's about the same because nitrogen is a molecule. So the cross-section per atom is almost the same. The number of atoms you need to destroy your molecules will be the same. And it will not be changing with energy. So in principle, it would be possible to go to lower energies. And as I already said earlier, when you go to lower energies, the disturbance of the beam by the interaction with the stripper gas takes over, gets more severe. And this you can see here when you say, okay, I have a beam which can be accepted from a spectrometer which has an acceptance angle of about 30 millirad. Then I would lose about 35% if I would use nitrogen as the appropriate density to destroy the molecules at beam energies of about 100 keV. With helium, it's different. I would lose only 7%. So much better conditions. And if I go even further down to 50 kilo electron volts, it would be absolutely impossible to do it with nitrogen, but with helium, we would expect to lose only 20%. And based on this idea, we just decided to build an instrument, which is, in practical, has the same design as the accelerator-based system, but in the middle, we have no accelerator anymore. We just have a molecular dissociation unit, a tube which is filled with gas, where we shoot the ion through and destroy the molecules. And this is always some kind of part which goes in parallel with the production of other instruments. And you see, this is a picture of this proof of principle experiment we done, and that's a real physics experiment. You see here wooden plates and tapes, and so it's, we really made it in a way from the components which were dedicated for these instruments in Spain and Hungary. We just collected the two low energy sites and combined it with a molecular dissociation unit just to see, is it possible to destroy the molecules and really detect C14. At these low energies, we can't go with the normal detection technology we are used to. We are using gas ionization detection, so we need some kind of other detection systems, but they are available from the mass spectrum, from the traditional mass spectrometry technology. So what we observed is that we could really identify C14 atoms with this system. You see on this plot, we scanned, that's the system, the ion source, the first mass analysis, the destruction chamber of the molecules, and then a second mass spectrometer of two components, a magnet and electrostatic deflector. And you see here, we changed the energy and also the magnetic rigidity. And we could really identify these C14 atoms from a standard sample which has about 1.3 times the modern concentration of C14. And this purple ocean around is at the level of 10 to minus 15. So even at 50 kilo electron volts, we are able to detect this. This is shown here for two different kinds of samples where we measured the counts of of mass 14 atoms as function of the density of the collision cell. And you see, for appropriate density, we end up with a nominal value, C14 atoms in the sample. For a sample which is not containing C14, we reach the 10 to minus 15 range, and this covers the whole region which is applied for radiocarbon dating. So in principle, this system will be working, and it will be working in the future. We tested even more in a way that we used known age sample material and did a calibration line, so what kind of dating is possible or can be done. So that's a proof of principle experiment we did last year, and we could really demonstrate that with those new type of instruments, in the future, C14 dating will be possible. We have used our, of course, you know, when you have done this, we had to disassemble all these instruments and ship it to Hungary and Spain. And yes, we wanted to continue our experiment, and we built a new device. And this device is now operational since early summer this year. So we have the same setup in principle, but we did not design the system as a working instrument. We designed it in a way, just have it as an experimental platform to optimize these kind of processes which are involved in the detection of the beam. And it's not that easy. And the problem which comes along, you know, here you see here, let's say the ion optical calculation of the beam which goes through the mass spectrometer, and the key point is that we have to introduce in this point the stripper, and as soon as we introduce the stripper into the system, we blow up the beam. And you see that the dispersion of the electrostatic deflector broadens the beam here. We can refocus it by appropriate ion optical means, but we really have to optimize this kind of procedure, these kind of geometries. You can imagine that if the gas flow from this quite dense cell will end up in these spectrometry regions of the magnets, collisions can just scatter some ions which end up in the detection system and destroy, let's say, your background or your sensitivity of a system. One thing which is extremely exciting is that at these low energies, the yield of the 1+ charge state is more than 75%. Or 3/4 of all of these ions, they will end up in the 1+ charge state, which is much more than at the maximum of the 1+ in nitrogen. And so maybe we can, in a later stage, accept that our transmission through the instrument will be a little bit less. We will see this. So right now we are not so advanced with the present setup, but we are able to detect C14 counts at the level of 10 to minus 14. So in this case, or in this sense, we can say, yes, we have taken the next step, and in principle, these kind of systems will be in the future. And all this development you have in Zurich. You know, we have the original big EMS system invented in the early 80s, based on a 6 MV tandem accelerator. We still use this accelerator for different kind of ion species, the chlorine-36, which is interfered by sulfur, and sulfur does form negative ions. So in this case, we need beam energy to discriminate against the different species. We have the so-called Tandy system based on a 600 kV Pelletron accelerator, which we predominantly use nowadays for beryllium-10, calcium-41, aluminum-26, iodine, and all the actinides. We have these miCADA systems, and we have the new platform to do this. So this is the technical part of my talk, and now I think we have some minutes more about the application. So that's now you know, let's say, the art of dating, and now we do some kind of examples. Okay, in order just to give some common grounds, I would like to repeat a little bit about the production and the methodology of C14 dating in itself. So, you know, C14 is produced in the upper atmosphere by the cosmic radiation. And the cosmic radiation is consisting predominantly out of high energetic protons, and these protons, they collide with nitrogen, oxygen, or argon, and they produce a secondary component, neutrons. And these neutrons, they can be captured or can be in an NP reaction produce C14 from nitrogen-14. So that's a two-stage process. From the primary component of the cosmic radiation, it will end up with secondary neutrons, and they end up in C14. And this C14 is now being chemically reacted in a pretty complicated way, first to carbon monoxide, and then with this photo disintegration of the ozone part, where the radical OH is involved. And this radical is now able to produce a C14O2 in the atmosphere. And this is done when it's C14 carbon dioxide, it's equilibrized in the atmosphere. And from the atmosphere, it can go via photosynthesis in the biosphere or via dissolution in the hydrosphere in the oceans. And in the oceans, there are about 90% of all the C14 atoms which are produced, they are present in the oceans. Only 2%, 1 to 2% are in the atmosphere. Looking into the production rate, so the production rate of C14 in the atmosphere is pretty low. There are 2 atoms per square centimeter and second are produced in the atmosphere. And they are, of course, in balance with the decay. And this means in numbers that per second on Earth, about 0.3 milligrams of carbon are produced, 9 kilo per year. And this gives you directly the inventory. So the inventory is about 100 tons of carbon-14 in the world. By just measuring the isotopic ratio carbon-14 to 12, it's easily possible to just compute the stable pool of carbon, which is 65 10 to the 12 tons of carbon, which are involved in this biological cycle. So how do we link to this biological cycle? That's clear. CO2 is absorbed via photosynthesis from the plants, and from the plant it goes into the cattle, and from the cattle it goes in us. Or by drinking beer, we just get C14. So, yeah, it's important. You know, you think that's something I always tell the students. When you look in the movies and they go with the Geiger counters and go to Fukushima, and then they say tick, 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 tick. Each count is the decay of an atom. And then you compute the number of atoms which are decaying in your body. 70 kilo of man material result in 3 kilohertz of C14 decay, which makes so we all, in a way, active. Fortunately, at a certain point, we die. And then, you know, the clock starts running, and then the C14 is decaying, and yeah, the C14 is coming down. And what we only have to do is just to measure the amount of C14 remaining in the Ötzi, which is somewhere up there, and it's only 50% of what we have in the atmosphere, and so we can say, yeah, it's about 6,000 years since he died. That's the very basic of radiocarbon dating. And yeah, like always in nature, I already said it, the situation is not so easy. There are some kind of preconditions which needs to be fulfilled that we can do this. And in order just to go in the past, we need to know that the production would have been constant over the time we are looking at. And this, it's absolutely not clear, and it's absolutely not true, because the intensity of the cosmic radiation, which is the cause of the production of radiocarbon in the atmosphere, is changing primarily due to two effects. The first effect is the varying strength of the Earth's magnetic field, which shield the cosmic radiation, the Earth from the cosmic radiation, or the solar activity. Solar activity exports plasma into the interplanetary space, and with the plasma, they are the magnetic flux lines of the sun which are introduced in the interplanetary space, and these flux will shield us from the cosmic radiation. And then there are other things which happened quite recently, you know, since the Industrial Revolution, we are just blowing C14, carbon dioxide into the atmosphere, and these are significant amounts of material which we blow there. And since it's fossil material, all the C14 is decayed, so we just dilute the atmosphere with stable C14. Other things which are maybe more relevant in the more recent past are these bomb tests. In the 50s and 60s, there are huge amounts of C14 were produced by nuclear explosions, and they were injected in the atmosphere. So they just, you see, they just doubled the amount of C14 in the atmosphere in a few years, and this is an amount of C14 which is equivalent to about 800 kilo. 800 kilo C14 were injected into the atmosphere. A nice tracer experiment. We make advantage of it in a certain case, but we are, on the other hand, in favor with nature, or nature is in favor with us, so they give us a book to read how the C14 concentration in the atmosphere had been, and this book is made out of trees. As we all know, these trees are growing year by year from the inner part to the outer part, and as soon as the fibers are fixed into the wood, they are dead. You know, they are just cut off the atmosphere. So just by counting the tree rings, we can get a very nice absolute chronological timescale. This time scale can be extended from different trees living in certain times, because the pattern of the tree rings is driven by the climatic regimes they are living on. In a good summer, there was a big tree ring, and in a bad summer, there was a small tree ring. And this pattern you can find in many trees living at the same time at overlapping situations. So by matching these trees with the same ring pattern, you can just extend this absolute dating chronology over the lifetime of one tree. A tree is typically living about 200 years, but by finding old trees, and old trees like the tree which was found in Schlieren, 10,000-year-old trees, you know, just from excavations or just from gravel pits, they find old trees, and then you can just match the dendrochronological pattern to extend this. And this has been done, not with us, many people were involved, and they made a chronology, a calibration curve over the last 13,000, 14,000 years, where we have the so-called radiocarbon age, which is just based on the isotopic ratio, and it correlates to the absolute age from the tree rings. So I want to go a little bit more in detail into the last 2,000 years, and this is the calibration curve we have available. And when we want to make, let's say, a dating of an object, we take a sample we chemically purify the material in order to get the real material, which is representative for the object itself. And then we do some kind of age calculation. You make the measurements, C14 ratio, which can be translated just with the half-life and with the isotopic ratio into an age. And this age, of course, has some kind of uncertainty limit. In this case, I looked for a very nice part of this calibration curve at 1365 with an accuracy of about 25 years. And then we can just go down and see for the probability, let's say we say with a probability of 2 sigma, 95%, we know that the object which has this ratio falls into an age interval which is given here. When you're looking into this calibration curve, you see that there are very odd regions. And these regions, when you look a little bit closer, there are many regions of this kind, which makes it very difficult to make precise age calibration. Quite recently, it gets important, this age range in the end of the 8th century, and Japanese group, they made very precise and high-resolution dating measurements, C14 measurements in tree rings, and they found a quite substantial step, which is 1.2% of rise in C14 concentration in the atmosphere within 1 year. And this was, of course, very surprisingly, and the people, we in Zurich and other people in Mannheim, they looked in the trees not from Asia, but in the trees here from Central Europe, whether we could see this signal as well. And we could really measure the same behavior. And now there's a discussion how this amount of additional C14 had been introduced in the atmosphere. And there are some proposals from galactic gamma ray bursts or from energetic solar particles which could do this. Of course, you know, it would be twice as much as a normal production would be required for 1 year to make such a big step. The big step which you see here is now very prominent, and it's prominent because we reduced the ability of making measurements at the uncertainty level of about 1 to 2 per mil. 10 years ago, 1%, 5 per mil measurements were a good number. And so we could reduce this, and we find, in a way, very exciting features in the calibration curve which are related to other things and give information, let's say, of the behavior of the sun or whatever in the universe. I will concentrate a little bit more on this region last 350 years where it's always said that in this period it's impossible to make dating measurements. And you see here the calibration curve, and the reason for these kind of fluctuations are related to the sun. The so-called Maunder minimum of sunspots were observed in 1650 to 1700, and there was a period where the sun was absolutely quiet. No sunspots were observed. And when the sunspots are missing, no plasma material is introduced in the space, and we are not shielded from cosmic radiation. So the production is rising, the production of C14 is rising, which means that the material gets more C14, and this makes it, in a way, younger. It has more C14 than it should have. So it gets younger, and then the calibration curve gets down. There was a smaller minimum of sunspot in the 19th century, which was called the Dalton minimum. And when you look in the first 50 years of the last century, you see this increase, and this increase is just caused by the dilution of the atmospheric C14 by the fossil CO2 we are producing, burning coal and oil. In general, people say, you know, if you have an object coming from this time, it's hopeless to make an age determination. But there are specific cases where you can still apply and get reliable dates, and I want to show you one example. And this example is related to the Studienwochen we are doing. You know, we invite pupils from high schools and say, come to us and learn about C14 dating. And then we encourage them just to bring some material from their personal life. You know, just bring something what you have, we will date it with you, and you learn how it works. And 2 years ago, or I think it was last year, when this guy, Christopher Binz, came and said, we have something in our possession, it's a fan, and this fan is a gift from Marie Antoinette. Marie Antoinette, you may know or not, you know, is the woman of Louis XVI, the last emperor of France before the French Revolution, and Marie Antoinette and Louis XVI, they were killed in the French Revolution. So, yes, but okay, this was a very nice example, and then we looked a little bit in the history books, and of course, yes, it was the case. You know, Marie Antoinette, she was married to Louis, but in a way which is called in proximity. You know, a French emperor would not have put any foot on Habsburgian grounds at that time. You know, they would not go there. So she married some other guy, you know, she was related to, instead of Louis, and then the whole bridal procession, you know, the whole community was moving step by step with 15, 20 coaches to Paris, and on this way to Paris, they stopped in a monarchy, Obermarschtal, where this family was living, and they made a big party, you know. And it was quite common that in this party some gifts were exchanged. So it's quite likely that this fan could come in the possession of this family. So we took a little piece of paper and dated it, and we made a very nice date, 190 years, with better than 3 per mil uncertainty. And if you can see what it means in respect of what age can it be, it could be of the 17th century, from the 18th century, or from the 19th century. So, in principle, yeah. But, you know, when you have additional information available, you can really improve this information. And you know, this fan was in possession of the family for the last, you know, it was from his grandmother, so they knew it was before 1900 in possession of the family. So you can just forget about this age range. And when you look into the style of the fan, how it was painted, from just art historic arguments, you can exclude the 17th century. And then you can just say, I integrate over this probability density and end up with a result which is very nicely falling into the area of Marie Antoinette. So the story is maybe not so wrong. Okay. I will give you another example from the same time, and this example has to do with the discovery of New Zealand. And New Zealand has been discovered at the same time, you know, 1770 by James Cook. And James Cook started a voyage for 3 years in the Pacific Ocean, and on his way he stopped in New Zealand. That's in history books. And but then there was a fisherman from New Zealand. He found a shipwreck in a very remote bay in New Zealand. And then he contacted some people from Discovery Channel, and they said, okay, yeah, we want to look at it. And yeah, and there were some kind of experts. They say, okay, this wreck looks like a Spanish caravel. And as it was used in the 16th century, so, and maybe somebody was there earlier than James Cook. So they took a part of the wood, and then they looked, of course, first in the dendrochronology. You know, you can match these tree rings and look in the record of all other trees and find the appropriate match. But this was not so easy possible, and from what the dendrochronology expert said, okay, it is of course oak and covering about 80 years, but could be France, could be 16th century. So what do we know from these many endeavors taking at that time? You know, Magellan was traveling north of New Zealand in the 16th century. Drake traveled between Papua New Guinea and Australia. Then there were two Spanish and a Portuguese sailor, which we sailed also near Australia. And Tasman, of course, who sailed through the southern oceans across Tasmania. And he also came across the shorelines of New Zealand. And in Delft, there's a floor where the shoreline of New Zealand is shown on tiles, but he never went on ground. He didn't take into possession the land for the Netherlands or for the Dutch. So our question was now to see whether maybe somebody in the 16th century would be the right discoverer of New Zealand. And so we decided to take this wood and sample it in a little bit different way. We took a first sample of 6 years in this time range here at the beginning of the wood. Then we counted 18 more years, took a second one of 5 years, a third one 14 years later, and the last one here in the center of the wood. And we did age determination, radiocarbon age, dating. And when you look now in the calibration curve, with this result, you have a clear match, you know, because we know between all of these 4 samples, there is a clear age relationship between the tree rings. It can only go in this time interval. This is a very nice and very precise result, plus minus 14 years. But unfortunately, the books of history have not been, or must not be revised, you know. So on the one hand side, you have a nice scientific result, but yeah, it's an example that with additional information, still this very strange period of time can be dated. And as a last example, maybe I have 5 more minutes, I will show you which is of interest for many of us. And of course, Mona Lisa is something which is very exciting. And earlier this year, there was a discovery of an example of Mona Lisa in the Prado in Madrid. And very recently, there was another one in the newspapers that there, this painting is also originating from Leonardo da Vinci and is a sister of her and so on. Actually, there are a number of copies of Mona Lisas in the world. I've just put quite a selection. Mona Lisa has different aspects, why it's so famous. Of course, it's from Leonardo da Vinci, and in this respect, it is a very specific piece of art. And when you look closer into the way it is made, you see that the background of the picture is a little bit fading away. You know, that's and Leonardo first introduced this technology of fading away the background to give it more Tiefenschärfe. So and so it's a clear art historic step in a way. So the other thing is, of course, it got lost in a theft in 1911, and then all these kind of different stories, why and where and so on, came up. But in the end, you know, there can only be one, the true Mona Lisa. But what is the true Mona Lisa? And we had some phone call from a guy. He said, I have a picture from a woman, and it's from an Italian master, and I would like to date it. And and then he came, to our lab, and I came with people from Weltifora and some security guys, and he brought this picture, and we just unpacked it, and we found it's Mona Lisa. So this picture we have from Jon Kreuger, or we have dated, is made on a wood panel. And of course, you know, we were expecting that it was not the real Mona Lisa, but we thought we could play the same game as we did with the wood from this caravel and exploit the age information. But it's on popple wood, and popple wood is very, very fast growing. You know, it's, and in the whole panel, we had only 5 to 8 years, and even with the best resolution, we have no chance of getting any correlation in between. But we took 4 samples at different locations, and we dated, and what we found, yeah, it's from the 15th century. Yeah? It's no doubt. This wood on which this material, this picture was made, is from the middle of the 15th century, perfectly matching with the time Leonardo painted it in 1506. And in addition to our radiocarbon analysis, other information was taken from this, so that these pigments from the colors were analyzed, and there were quite different pigments were used, which are, according to the expert opinion, would fit in the 16th century. So these are commonly used materials, like for instance, this lapis lazulus. It's a mineral from Afghanistan, which is a very rare mineral, and it's not easy to access, but good painters at that time were using it. Or lead tin yellow or lead white. You know, these kind of pigments were used. And also, that's another thing, you know, these colors were analyzed with ultraviolet light, and then you can see with UV light, you can see whether there are overpaintings on the painting, and to which degree the color itself has hardened. So they can say from the way the color is reflecting the UV light that it had been it must have been painted more than 80 years ago. And for 80 years ago, nobody really knew something about C14 dating. And why should somebody make a fake of a wooden panel by knowing maybe in 50 years people are able to make an age dating out of it? So this is quite puzzling, but it's not the end of the story. The end of the story was that it was examined by X-ray, and when you look a little bit more in detail, then you see here the face of Mona Lisa, and behind there is another portrait. So it's an overpainting. So this guy were taking away these wooden bars and looked for the different pictures, and these 2 faces came out. And then you can speculate who are behind Mona Lisa in this picture. Maybe it is Gianni Giacomo called Salai. He was a close friend of Leonardo, and he was a pupil of him, and there are some similarities. Or is it Ludovico Sforza, who was a Duke of Milano, and he gave several orders to Leonardo. And he was put out of power just at the early 16th century. And you see these signatures of his nose are maybe, I don't know, I don't know. In the end, in this case, it's clear there can only be one, but in the other case, there are more than one behind all these kind of things. And that's the laboratory of ion beam physics. We are about 30 people. We have strong support from the Department of Physics. We have strong support from our partners in the Earth Science Division, in the Institute of Particle Physics at PSI, EMPA, ERWAC, and we can sustain our activities in a very progressive fashion. So thank you for your attention.
Also entertaining talk. questions? Let me start with a short technical question. You explained about Coulomb explosion of the competitive molecules.
Yes.
Can one do that with lasers also?
Yes, in principle you can do this with lasers, but the problem is that the interaction time of these molecules in a laser beam are short because the ions are very swift, and this would require kilowatts of laser power. Of course, you know, they are available in short pulses, but we have DC beams, you know, they're coming constantly. So there had been several attempts using, let's say, it's not the decomposition in laser of molecules, but photodetachment of electrons. So to detach the additional electron of a species sulfur, for instance, in comparison to chlorine, where there's a big difference in binding energy, 3.6 versus 2 eV. But it's, yeah, the interaction time is too short to really use it.
Questions? Yes. Lima.
If you get some non-organic artifacts,
Yes.
can you date them?
Yeah, that's in a way we cannot date just iron. But let's say when these people, they were making their swords or their things, they were hammering together with coal. And in some of these iron pieces, there are coal inclusions. And if you're lucky to find these coal inclusions, you can date the coal inside. So that's some example where it's possible. Or let's say if you date mortar. Mortar is taking CO2 from the atmosphere while making the calcium carbonate. And then you can try to date the carbonate which comes from the atmosphere. But it's not that easy because the burnt calc, the degree to which it is completed from the original material is unknown. So you can have a mixture of the contemporary carbon dioxide from the atmosphere and the previous one which made the raw material of the mortar. This is, for radiocarbon, the only way of dating is via the organic material, in one or the other way. You know, it must have a link to the atmosphere. There are other ways of dating non-organic things just by the build-up of nuclides in, let's say, in a surface. If you have a rock surface which has been released from a rock fall, when there was a rock fall and the covering rock has shielded this rock from cosmic radiation. And if it falls down, you get a fresh surface, no radionuclides. And then you get the production from the cosmic radiation. And if you count the number of produced isotopes, you can say how long it has been exposed. So there are other ways of doing it, but not in a very general way as it is possible with organic material.
More questions, Renato?
To what extent can you get rid of these molecules by chemical treatment of the initial sample?
Yes, you purify the sample, but the molecules are formed in the negative ion formation process. If you just start from the beginning, you always have hydrogen in these things, and
so you cannot get rid of the hydrogen?
not at orders of magnitude, maybe factor 2 or less, but not 9, 10 orders of magnitude as required. Yes.
Geology.
Yeah.
How you are doing here? Because with radiocarbon, you more or less compare it with the trees.
Yes.
If you measure something which happens millions years ago, can you calibrate it?
No, this is not. There is no calibration for let's say dating of the increase of numbers of, you know, this in situ dating, you make, let's say, you establish the production rate, and then you average over much longer time scales. You know, you see that this 11-year cycle of the sun, which is modulating the solar activity, it levels out when you go over 1,000 or 100,000 years. So the production of nuclides, they are in a way more, let's say, more direct. Yeah, okay, as I said in the beginning, you know, from the 10 to minus 12, which we have contemporary, we can go back to 10 to minus 15. When these are a factor of 1,000, which is about 10 half-lives, 50,000 years. So that's the theoretical range of C14 dating. But when you prepare your samples, you know, in a certain, you take some material, you have to chemically treat it, and in all these treating processes, you introduce some kind of modern carbon. Tiny amounts, microgram size amounts of these carbon. And so the limiting factor is between 45, 48,000 years. So that's, but at that time, you know, we don't have the direct calibration. There we have to relate to a certain extent on other models. You know, we have no trees from that time, and there we have to go and look into other archives. There are other archives which extending further back. There are ocean sediments which can be dated with other nuclides, uranium, thorium, for instance, and then you can get an independent chronology. So, yeah. So about 50,000 years, 40, 50,000 years is what we can do.
Would it also be possible to take as an archive the ice and the polar cap?
Yes, for carbon, it had been proposed to do this. And what you can do, you can see when the snow is falling, it gets firn, and from the firn, at some certain point, the ice get closed, and you enclose atmospheric air. And people wanted to really date the C14 from these bubbles. If you retrieve an ice core from 3,000 meters below the surface in Greenland, you have only tiny amounts. So it's not so easy to do this, to get enough CO2 to do this. There are, in addition, other obstacles, because, you know, the first 100 meters of the ice core, maybe 50 meters, are an open system which are connected to the atmosphere. So you get a real mixture of you know, it's not so easy to have just this. And then there's another thing, that the cosmic radiation is producing C14 in situ, in the ice, you know, and this makes it very difficult to really use it as an archive. But for beryllium and chlorine, where there's a different kind of geochemical behavior, this is done. This is used as some kind of archive.
When you investigated the Iceman,
Yes.
was that in a smooth part of the calibration curve or a multi-value?
Yes, it is in a very, very, very odd part of the calibration curve. And actually, when you look at it, and you can say, within 200 years, we can really say when the Iceman was living. But that's the other point, you know. The further you go back in time, the less precise this information. You know, we don't know so much about this time, this prehistoric time. And so it doesn't matter whether it had been 4,500 before Christ or 4,300 before Christ. So, but it was in a very, very bad place.
How do you know that dinosaurs lived 100 million years ago, or this cow belonged to human only?
Yeah, this we don't know from radiocarbon. They are dinosaurs. They are not dinosaurs. You know, that's some geological time scales and geological, but mammoths and Niederwenningen, quite close to Zurich. There's a museum, and we dated the bones from the one which is about 40,000 years ago, and we have some kind of some material which is of that age in the lab. So if you want to come and see what we have, you're invited.
So what was your most amusing dating job?
You know, I have to say, you know, we are making about 4,500 measurements. And these examples which I showed you, they are, let's say, the most amusing one was for, we dated his beans from his house in the Kottero. Yeah. And we applied the same technology, you know, for wiggle matching, and we could really, but most of the things, they are related to climate exchange processes, deep water formation in the ocean, circulation things. So they are much more important things than I told you we do.
Okay, seem to be no further questions, so thank you very much, Hans-Arno, for the nice talk.